You've probably heard it a million times, right? In popular science, even from super smart physicists, time is an illusion. It's a seriously mind-bending idea. But what if it's just wrong? Today, we're going to dive into a totally different perspective, one that argues time isn't just real, it's one of the most fundamental things in our entire universe. So, yeah, time is no illusion. That's the bold claim we're digging into. The whole argument boils down to this. Time isn't some trick of our minds. It's fundamentally tied to change. And look, change is obviously real, right? Things happen. So if change is real, time has to be real too. So, how well does this idea actually hold up? Okay, so before we can even get to why we might need a new idea, we gotta talk about the reigning champion, the king of the ring for over 100 years, space-time. It's the model we think we know so well. Ever since Einstein, really, spacetime has been the standard model. It's the lens we use to make sense of everything: gravity, light, the whole cosmic shebang. And let's be clear, it has been wildly, unbelievably successful. I mean, you really can't argue with the success of spacetime. It's this beautiful idea that weaves space and time together into this single four-dimensional fabric. And here's the kicker. Every single experiment we've ever run has backed it up. It just works. But, and this is a huge but, there's a crucial little detail that we tend to gloss over. All of these confirmations, they're based on our perspective, a slow-moving human perspective. And right there, that's where the first little crack in this perfect picture starts to show. So you might be asking, if it works so well, what's the problem? Well, the problem shows up when you look at the fastest thing there is, light. This is where that nice, neat picture starts to get messy. You see, inside Einstein's own theory of relativity, there's this really weird rule. The faster you go through space, the slower time passes for you. And if you could hit the absolute speed limit of the universe, the speed of light, time would just stop. For a photon, a little particle of light, its clock doesn't tick at all. From its point of view, it experiences zero time. And right there, that's where the paradox kicks in. Okay, so here's the big conflict. On one side of the ring, you have relativity, telling us that a photon experiences no time. For that photon, being born in a star a billion light years away and hitting your eyeball happens in the exact same instant. It's instantaneous. But on the other side, we can see that photon change during its trip. It bends around a galaxy, its frequency can shift, it can get absorbed and re-emitted. It's clearly not static, things are happening to it. So that leaves us with this massive question, doesn't it? How can something change if, for it, no time has passed? It just doesn't add up. And this paradox is a huge hint that maybe, just maybe, our picture of reality is missing a piece. And that brings us to a potential solution. A completely different model for how the universe works at its most fundamental level. It's called the gliding universe. So here's how it works. Try to picture our entire three-dimensional space, everything we can see and touch, as a single sheet of reality. Now, this model suggests that this whole sheet is constantly, well, gliding along a fourth, deeper time dimension. As it glides forward, it's literally creating the future in front of it, and the past, the space it just left, just disappears. So what we call the present moment, that's just the very front edge of this incredible cosmic glide. So wait, does this mean we just throw Einstein and space-time in the trash? Nope, not at all. What this model actually suggests is that there are two different kinds of time. And the space-time we're so familiar with, that's just the one we're able to see and measure. The first kind of time, the deeper layer, is called machinery time. Think of this as the actual engine of reality. It's that fundamental one-way glide that's pushing everything forward. It's what drives all change everywhere all at the same time. And then there's the second layer, relativity time. This is basically just another name for the space-time we all know. But, and here's the key, in this model, space-time isn't fundamental. It's an emergent property. It's what slow-moving, complex things like us experience. We're just patterns moving way, way slower than the fundamental fabric of reality. So the time we measure, our space-time, is just our local, slow-motion measurement of the change being driven by that deeper machinery time. And this quote just puts it all together perfectly. Our clocks are slowly changing space change measurers. It's brilliant. What it means is our clocks, your watch, your phone, they aren't measuring that deep fundamental machinery time. They're just measuring local changes in space. The ticking of an atom, the swing of a pendulum. It's like we're measuring a shadow of the real thing. All right, so if we start looking at the universe this way, what does it all mean? What are the big consequences? Well, it turns out it gives us some surprisingly direct answers to some of the biggest questions we have.
So here are the big takeaways. First, change is real. It's not a trick, it's a fundamental part of reality. The universe is always in motion. Second, time is just the tool we invented to measure that change. So, because change is real, time has to be real too. It is not an illusion. And finally, this model makes a very clear, very firm statement on everyone's favorite sci-fi topic. Traveling to the past is physically impossible. Period.
So why is time travel impossible? Well, because in this model, reality isn't some static four-dimensional block of space-time that you can just hop around in. Think of it more like a powerful river. It's constantly flowing, constantly regenerating itself. You couldn't just make one tiny little patch of that river flow backwards, could you? No way. The rest of the river would just rush forward and immediately overwhelm it. The same goes for the fabric of space. And all of this leaves us with one last, really fascinating question to chew on. If this model is right, if we and everything we see are just these slow-moving patterns on a much faster, more fundamental fabric, it really makes you wonder, doesn't it? If our now is just a local slow motion effect, then what does the universe's true fundamental now actually look like? What's happening out there on that leading edge at the real speed of reality?